Hello everyone, we are going to discuss OPAMP as an inverting amplifier. In the last section, we learned the basics of the OPAMP and its properties. So we have the symbol of OPAMP like this. It has one inverting terminal and the non-inverting terminal is the output terminal. These two are the input terminals. So for non-inverting amplifier, we have to put some resistance, some signal. Suppose V I is a signal through some resistance R to the inverting terminal, and we are allowing some feedback. The feedback is such that some part of the output component is inside the input component through some resistance RF. So this is the feedback resistance. This value is the feedback resistance. So and the non-inverting terminal, the positive terminal, is grounded. It's a complete diagram of the OPAMP. So here we are considering 2 points. One is A, another is point B. One A point is here, B point is here. So the potential at A is equal to potential at A is equal to potential at B is equal to 0 as B is grounded. Why potential A and potential at B is equal? Because there is almost infinite resistance between the two input terminals. As there are infinite resistance between two terminals, so there is no practical current between the two terminals, and hence the potential at A is almost equal to the potential at B. So this concept is called the concept of the partial current. The concept of partial current. So we are going to apply the Kirchhoff's current law through this loop. So the potential across, suppose we have C, D. The potential across these A and B is equal to, it can be written as, suppose I current is flowing through it. So the potential will be I into V of F. If the output voltage is V out, then the potential difference will be V out minus V in. And the current flowing through this resistance is I, and if we replace it by RF, and we are getting the current flowing through the terminal RF. So that the current must be equal to the current flowing through RI. This is equal to VA minus VI divided by RI. This is basically, and is nothing, this expression is nothing but simplify this equation. Current through resistance RL is equal to current through resistance R. So the current through resistance RL can be written as this is the potential difference across the resistance RF divided by the resistance, and the potential and current through resistance RI can be written as the potential difference between the terminal of the resistance RI divided by resistance R. As we know, VA equal to VB. As you know, VA equal to VB is equal to 0. The concept of partial ground. I mean this concept. So applying this concept, we can write this equation as V0 by RF is equal to minus VI divided by RI. This implies naught divided by Vi, this is the gain basically, is equal to minus Rf divided by Ri. So we can control the gain by changing the resistance of the feedback resistance and the input resistance. By changing the resistance, the gain of the inverting terminal can be controlled. So in the case of inverting terminal, we are getting that the negative side with the input always and output voltage. So if we are applying some voltage in the input, the phase of the output voltage will be reversed. Will be 180 degrees shift. There will be 180 degrees shift in that phase. Now we are going to discuss about an OPAMP. An OPAMP as a non-inverting amplifier. OPAMP as a non-inverting amplifier. So for that, we are like the earlier case, we are taking the OPAMP, we are taking an inverting terminal and non-inverting terminal and the output terminal. As we are considering that as a non-inverting amplifier, so we are applying the voltage I here, and we are grounding the negative terminal through some resistance R. We are applying a feedback resistance R. So here is a question: why feedback resistance is always hit the negative terminal? Because the negative feedback is highly suitable and preferable because of the stability of the system. So negative feedback systems with negative feedback is highly stable. That's why we prefer negative feedback. So we are considering 2 points, A point and B point. So as the earlier concept, the voltage at A must be voltage at B. Here voltage at B is nothing but the input voltage here. So this is the our potential concept. We are going to apply this concept in this case also. So again we are going to apply the Kirchhoff's current law using Kirchhoff's current law. The current flowing through resistance RL must be equal to current flowing through resistance RF. Okay. So here the potential difference between the resistance is RL and RL is nothing but voltage VA minus 0. 0 because it is grounded divided by RL is equal to, suppose it is our output is V out, then V out minus V A divided by RF. So VA, the point VA is nothing but the VI, the input voltage. So here you just replace the VI concept here in place of the V A. So 0 we have plus this V now minus V. Next line VI divided by RL is equal to V naught divided by RL minus VI divided by RL. So this is RF. This is RF. So we are considering that VI term in a single side RL plus VI by RF. This is also RF. V naught by RF. So VI multiplied by RL RF. RL plus RF is equal Vi is equal to VL plus VF divided by RL equal to V naught. So V naught by VF is the gain actually, which we are going to define. Gain is nothing but RL divided by RF by RL. So this is 1 plus RF by RL. So unlike the inverting terminal, in non-inverting terminal we are getting the positive gain, and also the one factor is additional in this case. So in this in today's talk, we have discussed about the OPAMP as an inverting terminal and OPAMP as a non-inverting terminal. So thank you, and also we have also discussed about the concept of the partial potential